For more than a century, astronomers have known that the Andromeda Galaxy is not floating leisurely through the cosmos, but accelerating directly toward the Milky Way. When scientists first attempted to measure its motion in the early 1900s, they used a method called spectroscopy, which reveals how celestial objects move relative to us by analyzing the light they emit. In 1912, Vesto Slipher, working at Lowell Observatory in Arizona, pointed his telescope toward the distant spiral and noticed something startling. Andromeda's light was shifted toward the blue end of the spectrum. This phenomenon, called blue shift, occurs when an object is traveling toward an observer, causing the wavelengths of light to shorten and appear slightly bluer than they naturally are. At the time, Slipher estimated Andromeda to be barreling in at an incredible speed, around 300 kilometers per second, or roughly 186 miles per second, a velocity so extreme that if it were circling Earth, it could complete the trip around the globe multiple times within an hour. Later, refinements in observational technology improved the precision of that measurement, and modern data placed the approach speed closer to 110 kilometers per second, around 68 miles per second. Even so, that is astonishingly fast on cosmic scales. But determining motion in a straight line toward us is only half the puzzle. To predict whether a future collision might occur, scientists also needed to learn how Andromeda was moving sideways across the sky. This sideways drift, called proper motion, is much harder to detect at such an immense distance, about 2.5 million light-years, because any shift in its apparent position is unbelievably tiny when viewed from Earth. Imagine watching a coin move across a table from hundreds of miles away. That is the level of precision needed to detect Andromeda's lateral motion. For decades, astronomers could measure only the radial velocity and had no reliable way to determine whether Andromeda might pass by harmlessly, like a fast car speeding in the next highway lane, or whether it was locked on a direct trajectory toward us. The galaxy might have had a large enough sideways component that it would skim past the Milky Way, resulting in a dramatic near-miss rather than a head-on event. The uncertainty persisted well into the 21st century, leaving scientists in suspense about the ultimate fate of our galactic neighborhood. Then the Hubble Space Telescope delivered a breakthrough. Starting in 2002, Hubble repeatedly photographed specific star-rich regions of Andromeda, not aiming to capture the entire galaxy, but focusing on dense clusters where the positions of individual stars could be tracked with extraordinary accuracy. Over the course of 8 years, astronomers compared these stars against the seemingly immovable backdrop of galaxies billions of light-years away. Even the slightest shift in the foreground stars could reveal proper motion. By averaging thousands of careful measurements, researchers achieved sub-pixel precision, fine enough to detect movements smaller than 1,000th of an arcsecond per year. When the results finally arrived, they changed everything. In 2012, an international team led by Dr. Roland van der Marel analysed the data and announced that Andromeda's proper motion across the sky was effectively zero within the margins of uncertainty. In everyday terms, that meant the galaxy was pointed almost directly at us. The sideways drift, if any existed, was so minimal that it could not alter the outcome. Astronomers concluded that a major collision between Andromeda and the Milky Way was not only possible but inevitable. This revelation rippled through the global scientific community. Headlines declared that the two colossal spirals were destined to meet. Computer simulations illustrated dramatic future sky views, vast streams of stars stretching between the galaxies, tidal forces reshaping entire stellar neighborhoods, and a spectacular merging process that would unfold slowly over billions of years. These models predicted that the first close encounter would occur roughly 4 to 5 billion years from now, followed by gravitational rebounding and eventual coalescence into one enormous elliptical galaxy nicknamed Milkomeda or Milkomeda. For more than a decade, this scenario became the widely accepted expectation. The idea that our galaxy was on a cosmic collision course with the nearest giant neighbor fascinated scientists and the public alike. Documentaries visualized the future night sky filled with arcs of stars as Andromeda grew larger and brighter overhead. Textbooks confidently stated that the fate of both galaxies was sealed, and that gravity would ultimately bind them into a single entity. And in that era of certainty, the notion of Andromeda passing peacefully by seemed more like a discarded relic of earlier scientific caution. The consensus was clear. A direct collision was coming, and there was no escape. Just as the scientific world had grown comfortable with the idea that a Milky Way Andromeda collision was guaranteed, new observations arrived that forced researchers to rethink everything they believed about our galactic destiny. In 2025, a major study published in Nature Astronomy challenged the long-standing certainty, introducing a far more nuanced and surprising picture of the future. Led by Dr. Timo Sala and a team of astronomers from the University of Helsinki, the research reanalyzed the very assumptions that had built the earlier collision model. By combining fresh data about dark matter distribution, galactic mass, gas halo dynamics, and updated measurements of proper motion, the scientists concluded that the event everyone considered inevitable might not occur after all. What emerged was a scenario far more dramatic in its uncertainty. Instead of a guaranteed impact, the probability of a merger may be closer to a coin toss. Roughly 50% of predictions still show the two galaxies colliding, but the remaining half suggests Andromeda could slide by us without ever fully merging, coming close enough for gravity to dramatically reshape both galaxies, yet not close enough for complete unification. This conclusion shocked the astronomy community because it overturned more than a decade of confident modelling. For years, visualizations of the future sky depicted a majestic transformation that humanity, if still around, would eventually witness: Andromeda swelling into an enormous glowing feature dominating the heavens as tidal interactions stretched and twisted both stellar disks. Now scientists were forced to acknowledge that this vision might represent only one of several equally plausible outcomes, and that the long-accepted narrative of a galactic collision was perhaps an oversimplification. The new models show that even a very slight sideways motion could be enough to avoid a direct hit over cosmic timescales. The gravitational pull between the galaxies remains strong, but the future path depends on more than just the straight-line approach. Dark matter, still mysterious, invisible, and poorly understood, plays a critical role, because its vast halos add enormous mass that influences orbital dynamics. Even tiny uncertainties in dark matter structure can produce completely different predictions for the eventual encounter. If Andromeda's halo distribution is asymmetric or contains unseen substructures, those gravitational quirks could push its trajectory subtly off course. A tiny nudge, applied over billions of years, grows into a major rerouting. The new findings also explored the gravitational influence of the third largest member of our local group, the Triangulum Galaxy, M33. Previously considered too small to matter significantly in the Milky Way Andromeda destiny, M33 may actually act as a gravitational wildcard. Its orbit is complex and not fully stable, potentially looping around Andromeda or even joining the interaction between the two giants. Depending on how its motion evolves, M33 could either increase the likelihood of a merger or help redirect Andromeda so that only a dramatic near-miss occurs. What makes the new analysis particularly fascinating is how balanced the probabilities now appear. Scientists are not saying the collision definitely will not happen, only that it is no longer a certainty. The universe, it seems, is presenting two equally possible futures. That uncertainty injects a renewed sense of wonder into the question of our cosmic fate. For those who once felt uneasy at the idea of galaxies smashing into each other, there is now a comforting possibility of a gentler outcome. Yet the alternative scenario is no less breathtaking. The Milky Way could be reshaped by Andromeda's gravitational tide even if they never fully merge. Stars might be stretched into long, elegant streams. The spiral arms could twist and distort. New waves of star formation might ignite as gas clouds are compressed during the near pass. In this version of the future, the skies would still transform into an awe-inspiring spectacle. Close encounters without complete destruction. Crucially, whether the galaxies collide or merely dance past one another, the timescale remains immense. None of these events will unfold for billions of years. By the time either scenario begins to play out, the Sun itself will be approaching the end of its life cycle, expanding into a red giant and making Earth inhospitable, long before humanity could gaze up at the swirling lights of Andromeda filling the sky. This mismatch between astronomical drama and biological timelines reinforces a recurring theme in cosmology. The universe evolves on scales so vast that our place in the story is fleeting. But what made the 2025 discovery so impactful was not just the shift in outcome. It was the realization that the story is still being written. the cosmos is far more unpredictable and dynamic than any straight line of reasoning suggests. Even with cutting-edge instruments and brilliant minds at work, the future remains open, shaped by factors we are only beginning to understand. The comfortable certainty that once dominated scientific discussions has been replaced by something far more thrilling: possibility. For now, we must live with the knowledge that Andromeda may either crash into us or narrowly avoid full union. The universe has handed us a suspenseful cliffhanger that will take billions of years to resolve, and in that sense, the discovery reveals something profound, not only about the galaxies themselves, but about how little we truly grasp of the forces steering them through the dark. One of the most astonishing revelations in recent astronomy is the realization that the Milky Way and Andromeda are not actually waiting billions of years to begin interacting. They already are. For decades, the public image of Andromeda has been the glowing spiral easily found in the night sky as a faint blur, a neighbouring island of stars floating peacefully through the void. Yet this familiar view represents only the tinier central portion of the galaxy. Modern telescopes and advanced spectrographic techniques have exposed a much larger and more surprising truth. Andromeda is wrapped in a colossal invisible cocoon of diffuse, superheated gas that stretches outward for well over 1 million light-years in every direction. This halo, completely undetectable to the naked eye, is far bigger than the bright disk of stars we can see, and in some directions it extends almost all the way to our own galaxy. The scale of this structure is difficult to comprehend because it challenges every intuitive assumption we have about what a galaxy looks like. When we imagine a galaxy, we picture a lens-shaped swirl of stars, dust and nebulae. But the visible part of Andromeda is only the luminous heart of a titanic system that sprawls through far more space than we once imagined. The halo consists of incredibly thin plasma, so diffuse that even vast volumes contain very little material, yet its total mass is staggering, comparable to half the mass of all the stars shining within Andromeda's disk. Scientists now understand that this gas is a kind of galactic atmosphere, a reservoir of raw material that continuously feeds star formation over billions of years, as well as a repository for metals expelled from ancient supernovas. Because the halo's gas is spread out so thinly, it emits no light that telescopes can directly capture. Detecting it required ingenious methods, like watching how the halo absorbs tiny slices of light from quasars, brilliant beacons powered by supermassive black holes located billions of light-years behind Andromeda. As the quasar light passes through the halo, certain wavelengths are filtered out, leaving delicate spectral fingerprints that reveal the gas's composition and extent. Through this clever technique, astronomers have mapped the boundaries of the halo with unprecedented detail and discovered that it reaches nearly 1.3 million light-years in our direction. Our own galaxy has a similar halo, equally invisible, equally immense. When you place the two together and consider the distance between the Milky Way and Andromeda, around 2.5 million light-years, the conclusion becomes unavoidable. These halos overlap. In other words, our galaxies are already touching. Not in the dramatic sense of stars colliding or tidal arms ripping apart spiral structure, but in a subtler, quieter way that is easy to overlook yet cosmically profound. The leading edges of the two systems have begun to mingle, exchanging particles in a slow, delicate interaction that marks the true beginning of their long destiny. The collision has not only been predicted, it has technically already begun. Picture two massive whirlpools in an ocean, separated by a great distance. Long before the swirling watercores physically meet, the currents between them begin to shift and mix, quietly altering the flow. The halos of Andromeda and the Milky Way behave in a similar fashion, their diffuse gases responding to mutual gravity, drifting, stretching, and subtly influencing one another. Over millions of years, this exchange will intensify as the main bodies of the galaxies continue to move closer. Though stars remain untouched for now, the first threads of contact have already been woven. This realization forces us to rethink how galactic collisions truly unfold. The spectacular merging displays shown in simulations represent only the most visible climax, but the narrative begins in silence, with unseen matter reaching forward in anticipation. Humanity, without knowing it, is already living inside the earliest chapter of this grand cosmic encounter. It may take billions of years for the dramatic stages to unfold, but the opening act is in progress this very moment. the two greatest structures in our galactic neighbourhood have already shaken hands. Nothing about the night sky suggests this monumental connection. When we look toward Andromeda, its visible disk is a fragile-looking smudge, faint enough to disappear in a slightly light-polluted sky. It appears tame, distant, harmless, yet the truth is that the universe beyond our senses is alive with enormous structures and powerful forces interacting even when we see nothing out of the ordinary. Our galaxy is not isolated in the quiet black. It is already participating in one of the most extraordinary astronomical events imaginable, the gradual unification of two colossal star cities. The halos serve as the frontier of this merging process, a boundary that has already fallen away. What comes next is a slow but unstoppable journey toward deeper interaction, driven by gravity, guided by physics, shaped over time spans that make human history feel like a brief flicker of awareness. We are passengers in a galaxy that has already begun a long-distance embrace with its closest giant companion, setting the stage for a transformation that will, one day, change everything. The groundbreaking discovery of Andromeda's colossal halo didn't come from simply pointing telescopes at the galaxy and hoping to glimpse faint gas. Instead, it was the result of a highly coordinated research effort known as the Omega Project, short for Absorption Map of Ionized Gas in Andromeda, which used one of the most ingenious observational strategies ever employed in galactic astronomy. Rather than trying to detect the gas directly, scientists allowed it to reveal itself by how it interferes with light from distant quasars lying far beyond Andromeda. These quasars, powered by titanic black holes devouring matter at their centers, shine as some of the brightest objects in the universe. Their intense beams of radiation travel across billions of light-years of space before reaching us. When this light passes through Andromeda's otherwise invisible halo, certain wavelengths are absorbed by the atoms and ions suspended there, imprinting subtle dips in the spectrum that instruments can detect. By studying dozens of quasars positioned behind various regions of the halo, astronomers were able to build a three-dimensional map of its structure, density, and chemical composition. The findings were far more dramatic than expected. Instead of a thin veil around the galaxy, they uncovered an immense reservoir of plasma and ocean, of diffuse, superheated particles that stretches up to 1.3 million light-years outward in some directions, and nearly 2 million in others. That means Andromeda's full diameter, when the halo is included, is not merely twice the size of the Milky Way's stellar disk. It is more like 20 times larger than what the naked eye leads us to believe. If our eyes could perceive such diffuse light, the galaxy would dominate our sky every night, stretching from horizon to horizon, easily dwarfing every other celestial feature. The scale is so massive that our minds struggle to truly picture it. But discovering the halo's size wasn't even the most shocking part. When researchers calculated the amount of matter contained within it, they realized that the halo holds at least half as much mass as every star inside Andromeda's bright spiral disk. That means the majority of the galaxy's baryonic or normal matter is not in the stars at all, but floating in this gigantic envelope of gas. Much of that material is enriched with heavier elements, oxygen, carbon, nitrogen, and more created within stars and later expelled in supernova explosions. Over billions of years, countless stellar deaths have filled the halo with the byproducts of nuclear fusion, shaping a chemical legacy that extends far beyond the visible disk. In effect, the halo is a historical archive of the galaxy's life story, and a warehouse of the elements needed to build future generations of stars and planets. Andromeda is not simply a static island of light, it is a living ecosystem continuously recycling its own matter. This revelation dramatically changed astronomers' understanding of how spiral galaxies evolve. It showed that the visible disk alone cannot explain star formation rates or chemical distribution. The halo acts as a massive supply line, delivering fuel where needed and collecting the debris of stellar evolution. Its existence also helped solve a long-standing astrophysical mystery, the missing baryon problem. For years, astronomers knew that theoretical models predicted galaxies should contain more ordinary matter than they could account for in stars and dust alone. Where was the rest? In Andromeda's case, the answer was floating unseen in the halo the whole time. Yet despite the halo's richness, its density is staggeringly low, much emptier than the best laboratory vacuums on Earth. If you scooped up a volume the size of Earth's atmosphere, you would find almost nothing inside. And still, Across such enormous distances, those nearly non-existent particles collectively outweigh billions of suns. It is a profound reminder that the universe operates on scales overwhelmingly beyond everyday human intuition. The Omega project didn't just map a structure, it reshaped the entire narrative of Andromeda. Overnight, astronomers had to rethink what a galaxy truly is. And when they compared this vast halo to what we know about our own Milky Way, the realization struck: our galaxy must possess a similar, equally staggering envelope. Suddenly, the space between us and our neighbour didn't look so empty. The two giants were already intertwined at the edges, their halos blending like the outer atmospheres of planets brushing together in the void. What once appeared to be a distant relationship was revealed to be an ongoing connection. The collision story was no longer only about the future. It was also about the present. The invisible meeting we can't see with our eyes has been silently unfolding for millions of years. Every new bit of data pulled back the curtain further, revealing a cosmic relationship far more intimate than anyone imagined. And for astronomers studying the long-term fate of the local group, this halo mapping represented a pivotal moment. It transformed the way we predict and visualize the ultimate encounter between the Milky Way and Andromeda, showing that the forces bringing them together are already at work, shaping their shared destiny in the darkness between the stars. The realization that the halos of the Milky Way and Andromeda are already overlapping represents a profound shift in how we understand galactic interactions, because it means that the first stage of a collision does not begin with a spectacular burst of visible destruction, but with something far quieter and almost impossibly subtle. Instead of stars smashing together or spiral arms violently tearing apart, the earliest interaction is a gradual blending of faint superheated gas drifting at the fringes of both galaxies. These halos behave like the outer atmospheres of entire star systems, reaching across what once seemed like empty space and pulling each other into a mutual gravitational embrace long before the bright, dense cores begin to draw near. Although the gas is so thin that you could travel through a region the size of our solar system and still encounter almost no particles, gravity's influence accumulates across the vastness of those structures, tugging gently at every ion and molecule. Over millions of years, these tiny tugs add up, altering the motion of the gas and setting it on slow trajectories inward, like two cosmic tides beginning to feel the pull of a neighbouring shore. At this stage, nothing appears different when we look at the night sky. Andromeda remains a fragile smudge barely discernible to the unaided eye, while the Milky Way continues to stretch across our sky in its familiar glowing band. The colossal forces at work cannot be seen in starlight because the process is unfolding inside domains invisible to human senses. Yet the physics is already in motion, shaping a future that cannot be fully prevented. Gravity, once it links two objects, does not simply let them drift apart again. It will continue drawing them closer unless some extreme external influence intervenes, and nothing in the local group is large enough to break that connection. If we were able to observe the space between the galaxies through a magically enhanced vision tuned to detect thin halos of plasma, we would see something astonishing. The two galaxies do not feel like strangers slowly approaching each other, but like systems already sharing a permeable border. Imagine two enormous soap bubbles floating toward one another in slow motion. Even before their glossy surfaces touch, the air pressure between them begins to shift, the shapes distort, and each bubble senses the presence of the other. The halos are those surfaces' flexible boundaries responding to unseen forces long before any visible structures collide. And just as the merging of soap bubbles happens quietly at first, with almost no fanfare, so too does the earliest merging of these halos unfold in silence. There are no explosions, no bright flares, no signs of chaos that a casual observer could witness. Yet this stage is dramatically important, because it marks the beginning of a domino effect that will eventually involve the galaxy's visible regions. The gas exchanged in this early overlap might one day fall into denser parts of the galaxies, sparking waves of star formation or influencing how spiral arms evolve. And while the halos themselves appear calm, their particles are constantly bombarding each other at incredible speeds, heating up, mixing, and sometimes radiating faint energy, detectable only with sensitive instruments. The interaction zone between the galaxies could contain complex and evolving structures, rivers of gas, temperature gradients, and subtle magnetic fields, each shaped by two titanic systems slowly converging. This early overlap is also a reminder that even when the universe seems still and unchanging to us, it is actually alive with movement and transformation on scales too large to observe in a human lifetime. The galaxies are like ancient giants locked in a dance that spans billions of years. We, the fleeting inhabitants of a single planet orbiting a single star, are witnessing only the opening steps, unable to perceive the full choreography, but knowing it is underway. The fact that this merging has already begun reshapes how astronomers tell the story of our cosmic neighbourhood. Instead of saying the galaxies will collide someday, we now say the collision process is ongoing. We are no longer waiting for the event to start. We are living inside its invisible frontier. With every passing moment, the distance between the galactic cores shrinks, infinitesimally but inevitably. Though stars remain untouched for now, the halos act as a handshake across the void, binding the fate of both galaxies together. Future stages will be far more dramatic, with tidal forces stretching stars into streamers and gravitational slingshots flinging some systems into deep intergalactic exile. But even those dramatic chapters begin with this quiet prologue. The universe rarely leaps into chaos without first writing a long introduction. The intermingling of these halos is that introduction, subtle, slow, and immensely powerful. It is the moment where destiny takes shape, long before the spectacular consequences become visible. In a sense, our galaxy has already begun the journey toward transformation, and although the night sky looks unchanged, the future is already woven into the unseen space around us. Trying to grasp the distance between the Milky Way and Andromeda requires stretching the human imagination to its limits, because the numbers involved are so large that they lose all meaning when expressed merely as miles or kilometers. Astronomers estimate that the two galaxies are currently separated by roughly 2.5 million light-years, which means that the light we see from Andromeda tonight actually began its journey toward Earth when early humans were first learning to walk upright. If we attempted to convert that distance into miles, we would end up with a figure containing more zeros than anyone can intuitively visualize, about 15 quintillion miles, a number so vast that even comparing it to everyday travel does not help. If a car could somehow drive straight through the vacuum of space at highway speed without stopping for fuel, food, or rest, the trip would still require more than 40 trillion years, which is about 3,000 times longer than the universe has existed. Yet in the grand design of the cosmos, that separation is not immense at all. The Milky Way and Andromeda belong to a small community of galaxies known as the Local Group, a gravitationally bound collection that includes approximately 100 known members. Most of these galaxies are tiny dwarfs embarrassingly small, next to the two titans dominating the region. From a cosmic perspective, the Local Group is like a little island of matter floating in a much larger cosmic sea, surrounded by vast voids where almost nothing exists. Andromeda is the closest giant galaxy to us, a neighbour so near that astronomers often refer to it as the Milky Way's sibling. Although it is still millions of light-years away, the truth is that this distance represents convenience more than isolation. At galactic scales, 2.5 million light-years is practically a handshake. Light can cross the gap in a small fraction of the universe's lifetime, and gravity feels no hesitation in reaching even farther. The motion of Andromeda toward us demonstrates that proximity. Everything about its trajectory shows it is not simply drifting through space randomly. Instead, the galaxy is plunging toward the centre of mass of the Local Group, the same gravitational well that the Milky Way is falling into. The two spirals are locked together in a mutual attraction, spiralling closer like dancers drawn into one another's arms. Our galaxy is not sitting still either. The entire Milky Way is racing through space at hundreds of kilometers per second, pulled by the combined gravitational forces of nearby structures. What looks tranquil in the night sky is actually a scene of perpetual motion. Even the constellations we think of as fixed pictures are shifting over thousands of years. But galaxies move on a scale so enormous that their position changes are noticeable only across thousands of centuries. When astronomers first discovered that the universe is expanding, most galaxies were found to be rushing away from us, their light stretched into redder wavelengths. Andromeda is one of the rare exceptions in our visible neighbourhood. It is approaching rather than fleeing, its blue shifted light serving as a cosmic notice of its eventual arrival. That approach tells us that we are gravitationally linked and that someday the two objects will cease to be separate. Understanding distance in astronomy is therefore not just about measuring how far away something appears, but also about understanding how deeply we are connected to it. Andromeda might seem isolated visually, a lonely fuzzy patch embedded in the void, but its enormous gravitational reach guarantees that it influences us already. Our solar system, tucked inside the outskirts of a spiral arm of the Milky Way, is a tiny participant in a much grander cosmic relationship. The future of our galaxy is entwined with Andromeda's, whether that future leads to a graceful merging or an elegant near miss. For now, the vastness between us acts as a buffer, preserving the illusion of independence. People who look up at the sky see stars scattered serenely across the dark canvas, unaware that the entire tapestry is gradually shifting. Andromeda, though faint to the eye, is a colossal giant making its presence known not through light but through gravity. It is a neighbour so massive and so near that its influence shapes the dynamics of the local group as a whole. When we look at that faint glow so easy to overlook, we are actually seeing the single most significant external force acting upon our galaxy's future. The numbers may be intimidating and the distance is mind-bending, but the essence is simple. On the scale of cosmic architecture, the Milky Way and Andromeda are already neighbours sharing a mutual journey through space. Just as two ships drifting near each other on a vast ocean eventually interact through the pull of waves and currents, these galaxies are destined to meet. Quietly at first through their halos, and later more dramatically as the luminous components converge. The space between them, though immense, is merely the setting for a long and intricate gravitational ballet that has already begun. Our place in the universe is not static. We are part of a story that spans galaxies, written on scales far beyond human lifetimes. And even though Andromeda seems distant and gentle overhead, its approach is unstoppable, and its connection to us deepens with every passing moment, whether humanity is here to witness the result or not. The contrast between what we see of Andromeda in the night sky and what the galaxy truly is represents one of the greatest illusions in astronomy. To the naked eye, Andromeda appears as a tiny, pale smudge, so faint that many people can walk under it their entire lives without ever noticing anything unusual above them. It sits quietly near the constellation Cassiopeia, revealing almost nothing about its true scale or grandeur. Yet that faint blur is only the radiant core of an enormous spiral system. The luminous portion visible from Earth spans roughly 3 degrees across the sky, about 6 times wider than the full moon, though our eyes are able to capture just the bright central bulge. The spiral arms and extended star fields taper into invisibility, not because they are small, but because their light is spread too thin for human vision to register. In reality, Andromeda is among the largest structures we can see without any optical aid. If our eyes were capable of gathering more light, the galaxy would stretch outward far beyond its visible glow, revealing a majestic elongated disk that dominates a portion of the sky. Its physical width of roughly 200,000 light-years translates to a remarkable angular presence from our vantage point, making it one of the largest apparent celestial objects known, and that still ignores the full extent of its halo, which is so enormous that, if visible, it would engulf a vast region of the night sky, spanning more than 100 times the diameter of the moon. It would overshadow every constellation, dwarf the Big Dipper, and stretch from one horizon to the other, an ever-present giant cosmic window hanging overhead. The fact that none of this is visible to the unaided eye creates a deceptive sense of distance. Most people assume that if something looks small in the sky, it must be unimaginably far away. Yet Andromeda appears small, not because it is distant, but because human sight is blind to the faint outskirts that glow with light too weak to trigger our retinal receptors. The galaxy's vast star fields blend seamlessly with the background darkness, hiding a structure far larger than anyone would guess. This misperception is amplified by our limited intuition about astronomical scale. We are used to thinking of nearby objects as occupying large areas of visual space and distant objects as appearing small, but in astronomy, distance and size often conspire in ways that subvert simple expectations. Andromeda is so massive that even at 2.5 million light-years away, it still spans a large chunk of our sky-its shape stretched into a subtle ellipse, because we are viewing the galaxy at a slight angle rather than straight on. Our reliance on visible light alone also misleads us regarding what galaxies truly are. Even the brightest parts of Andromeda's disk are only the densest regions where stars cluster closely enough to form a cohesive glow. The outer regions are swarming with stars too scattered to overwhelm the darkness between them. The eye is a magnificent evolutionary tool but a poor instrument for cosmic detection. Telescopes, long-exposure cameras, and ultraviolet imaging reveal a breathtaking structure that stands in stark contrast to the unimpressive blur one might glimpse from a suburban backyard. In captured photographs, Andromeda's spiral arms unfurl like grand curving rivers of light. Pink nebulae mark the birthplaces of new stars, glowing with hydrogen emissions. Dark lanes of interstellar dust weave through the disk like delicate scars. The galaxy we can barely perceive with unaided sight becomes, through enhanced observation, a sprawling metropolis of suns numbering close to 1 trillion. And this is only the visible portion. The halo, invisible in nearly every amateur image, extends millions of light-years out and contains vast quantities of the galaxy's mass. If you could step onto a planet orbiting a star near the edge of Andromeda, the Milky Way would appear as a similarly impressive presence, a rival spiral dominating that alien night sky. The illusion of smallness is a trick played by light and the limitations of our senses. Andromeda is not a mere subtle splash of glow among the stars. It is a titan looming in our cosmic neighbourhood, close enough that even amateur astronomers can explore its beauty from Earth. Its enormous presence challenges our understanding of scale and distance, reminding us that what we observe is only a filtered hint of a much richer universe. Humans evolved under skies where perception was about survival, not star mapping, so our eyes show us only enough detail to navigate our immediate environment. The universe beyond that scope requires patience, imagination, and technology to reveal its truth. Andromeda looks small only because we are not equipped to see its greatness unaided. With the right tools and the right perspective, it transforms from a faint smudge into a living testament to the magnitude and wonder that surrounds our tiny world. Observing Andromeda from Earth is one of the most profound astronomical experiences available to the average person, precisely because it bridges the vast divide between casual stargazing and deep cosmic awareness. Despite its incredible size and importance, it requires remarkably little equipment to detect. The best time to locate it is during the autumn and early winter months in the Northern Hemisphere, when the galaxy climbs high in the night sky and remains visible for hours. On a clear, moonless night, far from city lights, the first step is to find the constellation Cassiopeia. Its distinct W shape makes it one of the easiest constellations to identify. Drawing an imaginary line from the innermost point of the W downward toward the constellation, Perseus will lead you almost directly to Andromeda's location. About halfway along that imaginary path, a faint blurry patch of light can be seen. That small smudge is the core of an entire galaxy hovering far beyond the stars we consider familiar. Even though the naked eye provides only the slightest glimpse, using binoculars immediately transforms the experience. The central glow becomes more pronounced, extending outward into a gentle oval. You begin to understand that it is not a star, not a nebula, but something vastly larger, a whole island of suns, hundreds of billions strong. Move up to a small telescope, and the view becomes even more compelling. 2 small companion galaxies, M32 and M110, appear like pale satellites flanking the main spiral. You may detect hints of the elongated disk and faint texture created by starfields and dust. With patience and good conditions, the galaxy reveals more complexity. Subtle brightness gradients, shifting tones across the structure, and in larger telescopes, indications of dust lanes cutting across the luminous background. The beauty of viewing Andromeda lies not in explosive colour or dramatic detail, but in the humility it evokes. The realization that the tiny glow in your eyepiece represents an entirely separate cosmic civilization of suns, worlds, and possibilities. Modern technology has made capturing Andromeda's splendour even more accessible. Amateur astrophotographers using digital cameras and basic tracking equipment routinely produce images that rival professional photographs taken a century ago. With long exposure times, the camera gathers light too faint for human vision to collect, gradually revealing the galaxy's arms unravelling into space like ghostly spirals. Hydrogen-rich nebulae emerge as radiant pink pockets where stars are being born. Dark lanes of dust snake across the structure, dividing starlight into intricate patterns. The result is nothing short of breathtaking, an image that looks like it belongs on a spacecraft's view screen rather than captured from a backyard. The reason Andromeda can be studied in such detail from Earth is its relative closeness. Most galaxies lie so far from us that even large telescopes can only resolve them as tiny smudges. But Andromeda is a neighbour positioned near enough that its features can be observed with surprising clarity. This makes it a crucial laboratory for understanding how spiral galaxies form, evolve, and interact with their surroundings. The study of Andromeda helps scientists answer questions about our own galaxy, since both systems share significant similarities in structure and composition. For scientists and sky lovers alike, the experience of observing Andromeda also carries a philosophical weight. To look at that distant glow with your own eyes is to witness ancient light, a message sent across space during humanity's distant prehistory. The photons entering your retina began their journey long before the construction of the pyramids, before the invention of language, before humans even knew how to make fire consistently. You're seeing Andromeda not as it is now, but as it once was, millions of years before modern civilization existed. The very act immerses observers in the deep time of the cosmos, reminding us that human history is a fleeting moment within a far grander timeline. The sight is also a glimpse of the future. That delicate smear of light is slowly swelling toward us. Long after the continents have shifted into shapes we would not recognize, long after species have risen and vanished from Earth, Andromeda will draw closer, gradually enlarging across the night sky. If intelligent life persists to witness the transformation, they will see a sight unlike anything in the history of our planet, a neighbouring galaxy stretching luminous arms from horizon to horizon. For now, however, Andromeda remains a quiet visitor in the sky, visible only to those who know where to look. Its presence is a reminder that we are not alone in the great structure of the cosmos. Our galaxy is part of a family, one that is slowly moving toward a dramatic reunion. Seeing Andromeda through any lens, even the simplest human eye, connects us directly to that cosmic story. The true scale of Andromeda becomes even more astonishing when we compare its physical structure to that of our own galaxy. For many years, astronomers believed that the Milky Way was the dominant member of the local group, boasting the greater number of stars and the more massive spiral disk. That assumption stood unchallenged for decades, largely because studying our own galaxy from within is remarkably difficult. Dust clouds obscure our view, and understanding our position inside the spiral structure complicates measurements. But as data improved, through more precise star counts, infrared observation, and analysis of rotational velocity curves, it became apparent that the earlier picture was wrong. Andromeda is not merely similar in size to the Milky Way, it surpasses it in nearly every measurable way. Its visible stellar disk spans roughly 200,000 light-years across, nearly double the Milky Way's diameter, and it contains around 1 trillion stars, more than twice the number found in our home galaxy. This immense population of suns forms tightly wound spiral arms, filled with star-forming regions and bright clusters. The galaxy's bulge, the central region packed with older stars, is also significantly larger and more luminous than the Milky Way's, hinting at a more active or collision-rich history. When the halo is included, Andromeda's full extent balloons to nearly 2 million light-years from edge to edge. That means the galaxy is not only twice as wide in visible stars, but potentially 20 times larger in its invisible domain of gas and dark matter. Andromeda is the heavyweight of our local cosmic neighbourhood. Scientists believe that dark matter plays a pivotal role in this mass advantage. Both galaxies are embedded in enormous halos of dark matter, the mysterious substance that exerts gravity but emits no detectable light. These halos hold the galaxies together, preventing the fast-moving stars in the outer regions from flying away into space. Measurements show that Andromeda's dark matter halo is particularly massive, perhaps even more massive than the Milky Way's, indicating that its gravitational pull dominates interactions within the local group. In simpler terms, Andromeda acts as the central anchor of our regional cosmic architecture, a gravitational monarch ruling over its surrounding galaxies. This imbalance in mass is a major reason the collision scenario has always seemed likely, because the more massive body tends to draw others inward. Andromeda's enormous structure also contains multiple smaller satellite galaxies orbiting it, similar to how the Milky Way hosts companions like the Large and Small Magellanic Clouds. M32 and M110 are the most easily visible of Andromeda's satellites, appearing as small elliptical patches of light near the main disk. These companion galaxies may have played a significant role in shaping Andromeda's form. Evidence from star streams' long ribbons of stars stretched across the halo suggests that Andromeda has consumed numerous smaller galaxies over time, absorbing their stars and tearing apart their original forms. The Milky Way is known to be cannibalistic as well, currently shredding the Sagittarius dwarf galaxy. But Andromeda appears to have pursued this feast with even greater enthusiasm. Every collision and merger leaves behind subtle signatures, distorted orbits, rippling spiral patterns, irregular rings that help astronomers reconstruct the galaxy's violent past. These forensic clues point to a history shaped by gravitational conquest. Surprisingly, Andromeda's superior mass does not necessarily make it a more stable or peaceful galaxy. In fact, larger galaxies tend to undergo more frequent and dramatic interactions. Their stronger gravity attracts more neighbours and more incoming material, giving them more opportunities to experience cosmic turbulence. The evidence strongly suggests that Andromeda has already endured multiple major collisions, each one contributing to the trillion-star empire we see today. The Milky Way has undoubtedly faced similar encounters, but Andromeda's scars seem deeper and more abundant. From a cosmic perspective, size determines influence, and influence determines fate. The enormity of Andromeda ensures that its gravitational pull shapes not only its own evolution, but also the destiny of the Milky Way. Even now, as both galaxies fall toward one another, Andromeda's greater mass will likely dictate the centre of the eventual system, positioning itself as the core of the future-merged giant. When that time comes, whether the galaxies collide fully or narrowly miss, Andromeda's scale will be a key factor in shaping the outcome. The stars of the Milky Way may be scattered into new orbits that wrap around Andromeda's expanding domain. Our familiar spiral arms may stretch and warp, becoming unrecognizable as they blend into a colossal new structure. In this sense, observing Andromeda is like looking at the future boss of our corner of the cosmos. It is not merely a point of curiosity in the sky, it is the dominant force that will one day transform the very night landscape we know. When we look at that faint blur from Earth, we are not just witnessing another galaxy. We are looking directly at the entity that will eventually reshape our own home. The immensity of Andromeda reminds us that the universe is not built around us, and that even massive structures like the Milky Way are subject to the greater currents of cosmic gravity. The collision course between the Milky Way and Andromeda is not a static situation, but an ongoing journey driven by the fundamental forces that shape the universe. When we say Andromeda is moving toward us, this does not mean that it travels in a straight, simple line like an object thrown across a room. Instead, the galaxy follows a complex path defined by the gravitational contours of the local group, influenced by the distribution of dark matter and interactions with surrounding dwarf galaxies. Andromeda is barreling toward the Milky Way at approximately 110 kilometers per second, fast enough to cross the distance from Earth to the Moon in just over an hour, yet at the scale of galaxies, this speed still translates into billions of years before contact. The universe operates on timescales that are almost impossible for the human mind to fully grasp. We measure our lives in decades, our civilizations in millennia, and our recorded history in a few thousand years. But galaxies evolve over epochs so long that continents can shift, species can rise and fall, oceans can form and disappear, and entire planetary climates can transform many times between major cosmic events. As Andromeda approaches, the night sky will undergo changes so gradual that no single generation will noticeably perceive them. But if we could compress billions of years into a time-lapse video, we would witness a breathtaking transformation. Andromeda would slowly swell in the darkness, expanding from a faint smudge into a glowing, structured disk, its spiral arms becoming increasingly clear as the galaxy grows brighter and larger. Eventually, Andromeda would dominate the sky, perhaps appearing as a magnificent double spiral alongside the Milky Way, creating a celestial panorama unmatched in beauty and scale. The approach would reach a point where the galaxies could no longer maintain their elegant shapes. Gravity would begin to distort their structures, tugging spiral arms into long curved streamers, flinging stars into elongated bridges between the two systems. This phase is known as the first close passage, a gravitational embrace that does not result in an immediate merger but dramatically alters both galaxies. Stars would be hurled into new orbits through gravitational slingshots, some ejected into deep intergalactic space entirely, destined to travel the cosmos alone forever. After the first pass, the galaxies would continue moving past one another, but would remain linked, losing kinetic energy to tidal forces. They would fall back together, colliding again in a more chaotic interaction. Eventually, after multiple passes and hundreds of millions of years, the galaxies would finally coalesce into a single, much larger system, an elliptical or lenticular structure sometimes nicknamed Milkomeda or Milkomeda, depending on the researcher's preference. From far away, this new galaxy would shine as a giant smooth orb of stars rather than the elegant spiral shapes familiar to us today. Interestingly, the individual stars inside the galaxies are so distant from one another that direct stellar collisions will be exceedingly rare despite the galaxies merging. The average separation between stars in a galaxy is so vast that it resembles scattered grains of sand drifting through an enormous volume of empty space. Instead, the drama unfolds as a gravitational ballet motion's altered, orbits rewritten, energy redistributed. While planets are unlikely to physically collide with other worlds, their destinies may nonetheless be dramatically changed. A star system like our solar system could be tossed into a new portion of the galaxy, pushed farther from the galactic center, or perhaps flung out entirely, leaving its familiar spiral home forever. All of these transformations are driven by the same invisible force that holds planets in orbit and shapes galaxies on scales of millions of light years: gravity. It is a quiet architect, patient and persistent, acting gradually but relentlessly over cosmic timescales. We exist during a calm moment of the universe's story, but nothing stays still forever. Our sky is not a permanent artwork, but a dynamic scene evolving beyond the pace of human observation. The fascinating truth is that the collision has already begun in the form of halo interaction, as discussed earlier. The visible spectacle lies far in the future, long after our species is likely gone, but the physics that guarantees this meeting is already in motion. Every second we live, the distance between the two galactic cores shrinks ever so slightly. The universe does not rush. It has no deadlines. Its transformations unfold at a tempo measured not in lifetimes but in eons. Understanding this future gives humanity a special kind of perspective. We are part of something immensely larger than ourselves, part of a cosmic relationship unfolding over billions of years. The sky above us is not frozen. It is a living narrative in which we are a momentary audience. To look at Andromeda is to see the future approaching slowly but unavoidably, written in the stars long before life ever appeared on Earth. Although the future collision between the Milky Way and Andromeda might sound catastrophic at first glance, the reality is far more nuanced and considerably less apocalyptic than one might imagine. Popular culture tends to portray galaxy collisions as violent cosmic smash-ups, where stars explode and worlds are destroyed instantly, but science paints a different picture, one where the scale of space prevents the majority of direct physical impacts. Stars, despite numbering in the hundreds of billions within each galaxy, are separated by such enormous distances that it is rare for any two to collide directly. The average distance between stars is so vast that even during a full galactic merger, the probability of any individual star hitting another remains extremely low. If the Sun were transported into the densest region of Andromeda, it would still likely remain isolated from other stars. Collisions that do occur tend to involve compact objects like black holes or neutron stars, but even then, these events are statistical anomalies across the total population. The primary drama of a merging galaxy pair occurs not among the stars themselves, but in the gravitational dynamics shaping their orbits. What will truly change is the architecture of both galaxies. The organized spiral structures will distort, elongate, and ultimately dissolve, as the systems are stretched and recombined by tidal forces. Yet life orbiting a star such as our Sun might never notice the chaos firsthand. Sunlight would continue to shine, planets would remain bound to their home star, and daily existence on any future inhabited world could remain surprisingly undisturbed at the personal scale. However, that does not mean the environment of the solar system would remain entirely unaffected. When the gravitational fields of two galaxies entwine, they pull stars into new trajectories that no longer resemble their original circular or elliptical orbits around the galactic center. Our solar system could find itself thrown into a more eccentric path, perhaps wandering farther out into the merged galaxy, or passing through regions of denser star populations. The sky might transform dramatically over time. New brilliant stars could appear, giant glowing regions of star formation could come into view, and the familiar corridor of the Milky Way could warp into a new pattern that future astronomers might struggle to recognize. Gas clouds, unlike stars, are far more prone to interaction. When galactic gas collides, it compresses, triggering bursts of star formation. This starburst phenomenon can create clusters of massive young stars, regions that shine intensely in ultraviolet light. Supernovae could become more frequent as large, short-lived stars race through their life cycles. Black holes at the centers of each galaxy may also interact, spiraling toward each other over millions of years before merging in a colossal release of gravitational waves. Such an event could ripple across the universe, detectable billions of light-years away by advanced observatories. This underscores a key difference between stellar and galactic scales. While most stars survive mergers intact, a galaxy's internal energy distribution, star birth rate, and central engine undergo dramatic transformation. Over time, the turbulence settles, and the merged system reaches a stable configuration, likely forming a giant elliptical galaxy without the elegant spiral structure we know today. That future structure, while less artistically sweeping, will be equally magnificent in its own right, shining brighter and containing more mass than either galaxy alone. Imagining the sky during various stages of this transformation offers one of the most astonishing thought experiments in astronomy. Tens of millions of years before the final coalescence, Andromeda will dominate the sky, appearing larger than any constellation. Spiral arms will become starkly visible, luminous arcs stretching across the darkness. Eventually, instead of two separate shapes, observers would see tangled streams of starlight weaving together into sprawling formations, as though cosmic brushstrokes are repainting the heavens. By the time the collision reaches its most chaotic stage, the sky might appear filled with enormous clouds of stars, dust lanes, and radiant knots of star formation glowing in blues and pinks. Night would become a celebration of light. And once the merging has completed and the new galaxy settles into its form, future inhabitants, if any survive the eons or evolve anew, would gaze upon a sky completely different from the one we know. They would live in a larger cosmic metropolis of stars, unaware of the elegant spiral that preceded their world's history and less preserved by their own scientific knowledge. In truth, the merging of the Milky Way and Andromeda is not a story of destruction, but one of creation and transformation. It is the continuation of a process that has shaped galaxies since the dawn of time. Collisions build larger cosmic structures, fueling starbirth and redistributing matter. Without such mergers, no galaxy would resemble the grand forms we admire today. The future of our galaxy, far from being doomed, is simply entering its next chapter, a chapter that began quietly through overlapping halos and will eventually culminate in a majestic unification written across millions of light-years. Even though this immense cosmic event is guaranteed by physics, humanity will almost certainly be gone long before the grand finale unfolds. The timescales involved stretch far beyond the lifespan of our species, our planet, and even our sun. Modern humans have existed for only about 300,000 years, a mere blink compared to the billions of years ahead, during which the Milky Way and Andromeda will continue converging. Civilizations rise and fall in the span of centuries. Entire species evolve or vanish within a few million years. Projecting forward billions of years requires accepting that everything familiar, the continents, oceans, and forms of life we know, will either be transformed beyond recognition or erased entirely by geological and cosmic processes. Our Sun, the source of warmth and life on Earth, is roughly halfway through its 10 billion year lifespan. Over time, the Sun will grow hotter as it converts hydrogen into helium, slowly swelling and brightening in a transformation that will eventually make Earth uninhabitable. Roughly 1 to 2 billion years from now, oceans will begin to evaporate, carbon dioxide levels will plummet, and the planet's surface will undergo catastrophic climate change. Long before Andromeda becomes a dominant presence in the sky, Earth may already be a scorched wasteland, incapable of sustaining complex life as we know it. Around 5 billion years from the present, the Sun will expand into a red giant, possibly engulfing the inner planets, including Mercury, Venus, and potentially Earth itself. By this stage, the first major interaction between the Milky Way and Andromeda may already be underway or imminent. If Earth still exists physically, its surface will be seared by the Sun's expansion, a barren rock orbiting a dying star. The fate of the solar system during the merger is uncertain. Our star could be flung outward into the edges of the new galaxy, or inward toward denser stellar clusters, where the night sky would blaze with countless bright suns. Or it could be ejected entirely, set adrift in intergalactic space as a solitary system, far removed from all galactic structure. In that lonely existence, the Sun and its remaining planets would wander endlessly through darkness, a cosmic exile disconnected from the grand merged galaxy. Yet these enormous changes, though dramatic on cosmic scales, would happen slowly, so gradually, that no single moment would feel like the arrival of disaster. If any form of intelligent life does survive long enough to witness Andromeda filling the heavens, it will likely be a species far different from humans, whether descended from us or emerging independently. Their understanding of the universe may surpass ours completely. To them, the merging galaxies might be a celebrated event, a predictable milestone in cosmic evolution, rather than an existential threat. They would know that collisions build new stars and create new opportunities for worlds to form. They might look at the expanding glow of Andromeda not with fear, but with awe and scientific curiosity. The merging of galaxies serves a fundamental role in shaping the cosmic landscape. Without such interactions, the universe would be populated largely by small, dim galaxies incapable of producing the rich variety of stars and planets we observe. Mergers mix material, feed central black holes, spark waves of starbirth, and generate structures from which new planetary systems emerge. The Sun itself may be the product of ancient collisions that occurred long before our galaxy settled into its current form. Life on Earth, therefore, owes its existence to the same forces that will one day erase every trace of our world. This paradox is woven deeply into the fabric of the cosmos. Destruction and creation are inseparable partners in the grand mechanism that drives galactic evolution. Considering these enormous timescales highlights how delicate and temporary our presence truly is. On a cosmic calendar, human existence occupies less than a pixel and ephemeral moment in a story billions of years long. And yet, in that brief moment, we have achieved something remarkable. We have looked up, noticed a faint smudge in the night sky, and learned that it is an entire galaxy on a path to join our own. Knowledge allows us to transcend the limits of time. Even if no human is alive to witness the merger, we can still predict it, model it, and understand its meaning. Astronomy gives us the power to comprehend the future long after our species has passed into memory. Our awareness of the collision connects us to a cosmic narrative that stretches across eras unimaginably greater than our lifetimes. The meeting of the Milky Way and Andromeda is not a threat to fear, or a tragedy to mourn. It is the next natural step in the ever-evolving architecture of the universe. Just as the galaxies have grown and transformed through countless prior interactions, so too will they continue evolving long after our chapter has ended. We are fortunate simply to know this story, to understand that the stars above us are not fixed in place, but dancing toward a distant union. In the end, the universe will continue writing its massive, slow-moving script, indifferent to the presence or absence of its brief observers. But while we are here, we can marvel at what is to come and feel the privilege of being conscious participants in a cosmos alive with motion and possibility. To better understand why galaxies like the Milky Way and Andromeda are destined to collide, we must explore the invisible framework that structures the universe, dark matter. Although stars, gas and dust form the luminous components of galaxies, they represent only a small fraction of their true mass. The bulk of a galaxy's mass exists in a mysterious form that cannot be seen directly and does not emit or absorb light. This substance, known as dark matter, reveals itself only through gravitational influence. It acts as the scaffolding around which galaxies form and upon which their shapes depend. Without dark matter, galaxies would simply fly apart because their visible mass alone is not sufficient to hold them together once they begin spinning. The rotational speeds of stars orbiting the centers of galaxies provide a critical clue. They move far faster than they would if only the observable matter were present. Something unseen must be binding them in. In the case of the Milky Way and Andromeda, Each galaxy is embedded in an enormous halo of dark matter, extending well beyond the regions where stars reside. These halos are so massive that their gravitational pull affects not only the structure and rotation of the galaxies, but also the motion of neighbouring systems. Over the course of billions of years, the gravitational dance between these dark matter halos becomes the dominant force driving the galaxies toward one another. Their halos are already touching, which means the galaxies are not drifting independently through space, but are gravitationally anchored together. The overlapping halos act like the early stages of a cosmic handshake, ensuring that the two galaxies will eventually merge. From the moment this contact occurred, which likely happened billions of years ago, the collision became inevitable. It is not a matter of if, but of when. This dependence on dark matter underscores a critical truth. The universe we perceive with our senses is only a small portion of what actually exists. Everything visible, stars, planets, nebulae, comprises less than 5% of the cosmic total. The rest is hidden in forms that do not interact with light. Because dark matter shapes the large-scale structure of the universe, even the fate of our galaxy is governed by something we cannot see. Without this unseen substance, Andromeda might have drifted past harmlessly into the void, and our galaxies would never have crossed paths. Instead, dark matter's pervasive gravity is pulling Andromeda relentlessly toward us, slowly accelerating the process as the distance narrows. Understanding dark matter also clarifies why galaxy collisions are such a common part of cosmic evolution. When the universe was younger and galaxies were more densely packed, interactions were even more frequent. Many of the grand spiral galaxies we admire today, including the Milky Way, owe their current shapes to previous mergers. Evidence of past collisions is etched into the motions of stars, the distribution of gas, and the distorted halos surrounding both galaxies. Andromeda's halo, for instance, contains long streams of stars, tidal remnants of galaxies it consumed long ago. These streams act like historical records, revealing a legacy of gravitational conquest. The Milky Way displays similar scars, including the Sagittarius stream, a river of stars ripped from a smaller galaxy currently being absorbed. This ongoing galactic cannibalism demonstrates that collisions are not exceptions. They are the primary drivers of galactic growth. Large galaxies become large by devouring their smaller neighbours, accumulating mass and shaping their architecture over billions of years. In this context, the upcoming merger is simply the next chapter in a long history of interactions. Dark matter directs these encounters as it weaves galaxies into vast cosmic webs, funneling them along gravitational filaments. On the grandest scales, clusters of galaxies form nodes where these filaments intersect, creating massive structures millions of light-years across. The local group, with the Milky Way and Andromeda as its giant anchors, is only a small example of this pattern. Both galaxies are falling slowly toward the Virgo cluster, a massive congregation of galaxies whose gravity influences even our distant corner of the universe. Everything is moving, everything is shifting, and dark matter serves as the quiet architect behind it all. What makes Andromeda's approach profound is not danger, but inevitability. We are witnessing the natural motion of galaxies through the cosmic landscape. Their merger is as fundamental a process as stars being born or planets forming around young suns. It is not chaos, but one of the universe's most elegant mechanisms for recycling matter and restructuring the heavens. Even though humanity will not witness the final stages, our understanding bridges that temporal gap. We comprehend the forces shaping our galaxy's destiny long before the spectacle becomes visible. In a way, knowledge grants us a kind of immortality. We can imagine the sky of the far future, illuminated by a galaxy that today whispers to us only faintly in the dark. The collision between the Milky Way and Andromeda is the product of forces set in motion at the dawn of time. Every star, every planet, every atom in our galaxy is participating in this grand gravitational migration. And though our portion of the cosmos feels stable and familiar, it is being guided toward transformation by the unseen hand of dark matter, shaping a future we can predict but will never personally see. To imagine what the sky might look like during the approach and eventual merging of the Milky Way and Andromeda is to stretch the human imagination into a realm of breathtaking cosmic artistry. Long before the galaxies physically interact, the view from Earth, or whatever worlds may exist by then, will gradually evolve into something grander than anything we recognize today. In the present era, Andromeda appears as a faint smudge, barely noticeable without guidance, but over the course of hundreds of millions of years, its appearance will shift inch by inch across the sky, growing brighter and larger as the distance between us shrinks. If intelligent beings exist to witness this transformation, they would observe changes so slow that each generation would regard the sky as fixed, never noticing how every century adds the slightest amount of detail to Andromeda's shape. However, if we accelerated time into a viewable sequence, the sight would be extraordinary. The spiral arms would gradually become visible to the naked eye, their sweeping arcs brightening against the backdrop of space. Eventually, Andromeda would dominate the night sky, dwarfing every constellation and making the Milky Way's own band seem like a modest ribbon by comparison. Instead of a small hazy patch, it would become a magnificent whirlpool of light spanning a significant portion of the heavens. The sky would no longer feel spacious and empty, but vibrant alive with the presence of a neighbouring galaxy reaching out across the cosmic gulf. As the galaxies draw closer, they will begin to warp each other's structures. Spiral arms will start to distort, stretching into elongated streamers and tidal tails that sweep across the sky like luminous strokes of a celestial brush. New stars will ignite in brilliant clusters as interstellar gas clouds collide and compress within the gravitational conflict. Nebulae may glow more intensely, while regions rich in young, massive stars shine in piercing shades of blue and ultraviolet. The night sky could shine with colours and radiance unlike anything ever seen by human eyes. During the first close passage, Andromeda's core might appear as a dazzling double nucleus alongside our own galactic centre, creating an unprecedented celestial vista. Two bright hearts of stellar concentration sharing the same sky. Stars pulled out of their native orbits may form glowing bridges connecting the galaxies, a cosmic archway of starlight stretching across unimaginable distances. It would be a spectacle of motion and transformation, with the sky itself becoming a theatre of gravitational choreography. Over millions of years, the sky would continue to shift in ways that would seem miraculous to anyone lucky enough to observe it consciously. The graceful spirals familiar today will begin dissolving into chaos as the galactic disks overlap and twist. New shapes, rings, loops, irregular plumes will emerge as the combined gravitational forces reconfigure the mass of both systems. The Sun, if it still retains its planets, might journey through new regions of the forming galaxy, encountering denser patches of stars or drifting into more isolated galactic suburbs. The view would continue reshaping, with star fields thickening or thinning depending on whatever new orbit the solar system acquires. Eventually, after the chaos settles and the galaxies complete their merging process, the sky will find a new equilibrium. Instead of seeing a spiral structure, future observers would look out onto a vast elliptical expanse of stars, smoother, rounder, and more uniform than the elegant spirals that once defined both galaxies. The merged system would shine brilliantly, its central regions crowded with the combined stars of two giant galaxies. Star formation may gradually decline as the remaining gas is consumed or dispersed, leaving behind a massive ancient stellar population that glows warmly for trillions of years. The night sky would still be magnificent, just in a different way, dense with light but lacking the distinctive swirling arms that now enchant astronomers. It is fascinating to imagine how the psychological experience of the night sky might shift for any future inhabitants. Our current sky inspires a mix of curiosity and humility. Its dark spaces convey vastness and mystery. In contrast, the sky of the merger era would feel dense and luminous, perhaps overwhelming in its brilliance. Instead of faint constellations, future beings might navigate by vibrant clusters and expansive streams of stars. Their myths, their science, and their understanding of the cosmos would be shaped by a sky that never once resembled the one we see today. Thinking about this future reminds us that even the heavens, so often seen as symbols of permanence, are undergoing constant evolution. The constellations we name and cherish are temporary alignments, destined to be twisted and erased by the flow of cosmic time. Orion will someday appear as a stretched and unrecognizable shape. The Big Dipper will disperse, and Andromeda will no longer be a distant blur but part of the very system we call home. The merger of our galaxy with Andromeda is not simply an astronomical prediction, it is a reminder that change defines the universe at every scale. Worlds transform, stars evolve, and galaxies reconfigure themselves in a continuous cycle of motion and rebirth. For now, we occupy a serene moment in this cosmic story, gazing upon Andromeda as a quiet messenger of both the past and the future. But the sky we know is merely a chapter one among many that the universe will write above our heads across the ages. To comprehend how Andromeda and the Milky Way will come together, astronomers rely heavily on detailed computer simulations, virtual universes built from physics and mathematics, capable of predicting the choreography of galactic encounters. These simulations incorporate everything from the gravitational influence of dark matter, halos, to the behavior of gas clouds under immense pressure. By inputting data such as Andromeda's velocity, distance, mass distribution, and trajectory, scientists can fast-forward billions of years into the future and witness the collision in a compressed span of mere seconds. Watching a simulation unfold is like viewing a time-lapse recording of a grand cosmic dance, where two immense spirals drift closer, then stretch and intertwine before finally merging. While all models confirm the inevitability of the meeting, the precise details differ depending on variations in input data. Some simulations depict a direct head-on collision, while others show a slightly off-center encounter that results in more pronounced tidal structures and multiple passes before the final merge. In each scenario, the galaxies undergo dramatic shape changes. Their spiral arms, once elegantly wound, become extended bridges and tails of stars flung outward by gravitational forces. The graceful rotational symmetry of each galaxy quickly dissolves as the collision robs them of their ordered motion. In some models, the Milky Way's disk tilts sharply, or warps like a bent coin, while Andromeda's central bar elongates and shifts off axis. Despite the intricacy of these transformations, the overall outcome is consistent. The disks cannot survive intact, and the system ultimately relaxes into a large elliptical galaxy. Simulations also allow astronomers to test how the solar system might fare during the merger. Because stars are typically so far apart, the Sun is unlikely to collide with another star. But gravitational interactions are unavoidable. The solar system may be slingshotted into a new orbit, perhaps moving farther away from the galactic core or out toward the newly formed halo. Some projections even suggest it could be expelled entirely, drifting alone through intra-cluster space as a rogue star system. Other models show the Sun passing near dense star-forming regions, leading to skies filled with young, brilliant suns, unlike the sparse star fields we see today. It all depends on the precise pathways the galaxies take as they fold together. Another key insight gained from simulations involves the central black holes of both galaxies. The Milky Way's supermassive black hole, Sagittarius A, has a mass of about 4 million suns, while Andromeda's central engine is several times larger. When the galaxies merge, their black holes will sink slowly toward the new galactic center due to a process known as dynamical friction gravity, gradually draining their orbital energy. Over millions of years, they will spiral closer together, forming a binary system that orbits faster and faster until eventually merging into one even more massive black hole. The final coalescence releases an enormous burst of gravitational waves, ripples in space-time that travel outward at light speed. Future civilizations in distant galaxies might detect those waves and trace them back to the moment our galaxies became one. Through simulation, astronomers can also investigate how star formation evolves during galactic mergers. When gas clouds crash into each other, shock waves cause them to collapse, creating intense periods of star birth called starbursts. Simulations consistently show that the collision between the Milky Way and Andromeda will trigger such starbursts, especially in the early stages. The night sky may be illuminated by clusters of hot, massive stars that burn quickly and die spectacularly as supernovae. These explosions enrich the galaxies with heavy elements, metals essential for forming planets and life. Eventually, as the gas reserves are consumed or scattered, star formation slows, and the merged galaxy settles into a quieter existence dominated by long-lived older stars. What makes these simulations so important is that we cannot rely on direct observation to learn about events unfolding over billions of years. Human lifespans are far too short, and even the recorded history of astronomy is only a fraction of the needed timeline. Computers allow us to condense monumental epochs into comprehensible visual stories. They give us a preview of the sky our galaxy is moving toward and reveal the stages of transformation that will reshape its structure. Simulations are constantly improving thanks to advances in computing power and observational data. The Gaia mission, for example, has provided unprecedented measurements of millions of stars in the Milky Way, refining our understanding of the galaxy's motion and gravitational field. As we gather more accurate information about Andromeda's movement, including sideways velocity known as proper motion, the predicted collision dynamics become more precise. What once was speculation has evolved into a sophisticated scientific forecast backed by ever-growing evidence. In a way, these simulations serve as the universe's autobiography records, not only of the past but of the unwritten future. They show that our galaxy is not an isolated island, but part of a grand cosmic ecosystem where interactions shape destiny. Watching the Milky Way and Andromeda collide in simulation is both humbling and exhilarating. Humbling because it reveals our small role in the universe, and exhilarating because it shows we can understand cosmic events far beyond our temporal reach. Knowledge becomes a bridge connecting humanity with epochs we will never witness, allowing us to stand, however briefly, in the presence of cosmic time itself. One of the most captivating mysteries emerging from studies of the Milky Way and Andromeda is the possibility that their eventual merger will not happen in isolation, but as part of a larger transformation within the local group. The local group, although modest in astronomical terms, contains a collection of smaller satellite galaxies that orbit the two central giants. As the Milky Way and Andromeda move toward each other, their gravitational grip over these smaller systems will tighten as well. Over time, many of these dwarf galaxies are expected to be absorbed into the merging structure, contributing their stars and dark matter to the formation of an even more massive galactic remnant. For example, the Triangulum Galaxy, M33, the third largest member of the local group, may play a significant role in the interaction. Current observations suggest that Triangulum is gravitationally bound to Andromeda, and simulations indicate that it could either collide with Andromeda first or join the three-way dance later, becoming part of the final merged system. Smaller galaxies like the Magellanic Clouds, currently companions of the Milky Way, may fall inward and be consumed along the way as well. This means the future galaxy will not just be a union of two giants, but a conglomerate assembled from a wide collection of star systems, an entire family of galaxies blending into one. Such mergers are the engines that build the massive elliptical galaxies we see sprinkled across the cosmos. They are not mere curiosities, but fundamental processes driving cosmic evolution. In fact, astrophysicists believe that nearly every large elliptical galaxy found in dense galaxy clusters is the product of multiple spiral mergers that occurred over billions of years. This trajectory reveals something important. The spiral shape of the Milky Way is temporary, a relatively brief period of aesthetic beauty in the life cycle of a galaxy. Spirals are active, star-forming systems with swirling arms fueled by gas dynamics. But when galaxies collide and their gas is consumed or scattered, the ordered rotation that defines spiral patterns collapses into more randomized stellar motion. The result is a rounder, puffier structure, one that may not possess the dramatic visual flair of a spiral, but carries its own quiet grandeur. The future descendant of the Milky Way and Andromeda will be such a structure, a giant, smooth, elliptical galaxy shining with the combined mass of trillions of stars. Astronomers often refer to this hypothetical object as Milkomeda, or the Milkomeda Galaxy, but whatever name future beings give it, its presence will redefine the identity of our cosmic home. The heart of this future galaxy will be exceptionally bright. With two supermassive black holes merging and central star populations crowding into dense environments, the core could become one of the most luminous regions of the entire galaxy. Close to this core, the night sky, if planets exist there at that time, would be ablaze with intense starlight, far brighter than anything visible from Earth today. Imagine stepping outside under a sky filled with stars so close and numerous that darkness would be rare. Some simulations suggest that after the merger, the solar system could find itself much farther from the galactic center than it is now, placed at the outskirts of the new formation. In that case, the sky might remain somewhat similar to the present, but with greater density in some regions, a reminder that although our system survived the merger, its cosmic address has changed forever. Exploring how life might adapt or observe such a transformed sky requires speculation, yet it highlights an intriguing idea. While galaxies undergo dramatic evolution, solar systems can persist and carry the potential for life far into the future. The cosmos is dynamic, yet persistent structures such as stars and planets can endure through chaos. The next chapter of the local group also touches on the fate of intergalactic space. Stars flung outward during the merger could roam freely for eternity, unbound to any galaxy. These orphaned stars will become faint travellers illuminating the otherwise empty darkness between cosmic structures. Some may host planets, and possibly forms of life, drifting like isolated islands in the deepest seas. The Milky Way Andromeda collision is therefore not just a merger, it is a grand reshaping of an entire region of the universe, redistributing matter and rewriting the structure of space itself. The name local group may one day become obsolete, because once the merger stabilizes, the new galaxy will remain gravitationally dominant over a vast region, with fewer independent members left to justify a collective title. The evolution of our cosmic home is part of the larger story of how structure forms, grows and disperses throughout the universe. Our galaxy's current appearance, while beautiful and iconic, represents a single phase within a vast timeline. In the distant past, the Milky Way was smaller and less organized. In the distant future, it will be larger, rounder, and perhaps more majestic in a different way. Nothing in the universe remains unchanged. Not stars, not planets, not galaxies, and not even the space between them. From this perspective, the merger with Andromeda is not an extraordinary event, but a natural progression, a transformation woven into the cosmic flow since the very beginning. As we contemplate the future merger between the Milky Way and Andromeda, we must also reflect on the broader significance of such events within the cosmic timeline. The universe, currently about 13.8 billion years old, is still relatively young when considered against the unimaginable durations it may continue to expand. In this ongoing story, galaxy collisions are not rare catastrophes, but rather routine milestones in the life cycle of cosmic structures. When the universe was much younger, galaxies were packed closer together, leading to frequent and often violent interactions. Over billions of years, these mergers helped sculpt the vast array of galactic shapes we see today. The Milky Way itself is not a pristine, untouched system, but a construction of many earlier collisions, each contributing stars, gas, and dark matter to the growing structure. Ancient star streams scattered across our sky are fossil evidence of past galactic encounters. Andromeda, too, reveals a cannibalistic past. Its outer halo contains remnants of smaller galaxies it has devoured, their stars stretched into long arcs by tidal forces. The truth is that the upcoming merger between our two giant spirals is simply the next phase in a grand tradition of cosmic assembly. Understanding this places humanity's concerns into perspective. We often imagine events in space as dangerous threats, as if the universe were plotting calamities directly against us. But mergers are not about devastation. They're about creation and renewal on a scale that transcends individual species and worlds. In fact, many of the most beautiful cosmic sights, glowing nebulae, clusters of massive stars, radiant starburst regions, owe their existence to the chaos unleashed by earlier galactic interactions. Without mergers, the universe would lack much of its dynamic character. It would be quieter, darker, and less fertile for life. Collisions stir things up. They ignite stellar nurseries and distribute heavy elements needed for planets and biology. The iron in our blood and the calcium in our bones came from stars that formed in galaxies shaped by ancient mergers. In a deep sense, we are direct beneficiaries of those cosmic collisions. This realization allows us to reinterpret the future of the local group not as a tragic fate, but as a continuation of the same cosmic processes that made our existence possible. In tens or hundreds of billions of years, when the newly formed Milkomeda Galaxy has aged and mellowed, it will shine as a massive elliptical system, grand and luminous, floating serenely within an ever-expanding universe. But here lies another layer of wonder. The accelerated expansion of the cosmos means that galaxies beyond our local neighborhood are moving away faster and faster. In the far future, after the local group's merger has settled, nearly all other galaxies will drift beyond the observable horizon due to cosmic expansion. Their light will stretch into wavelengths too long to detect, and they will effectively vanish from view. The merged Milkomeda Galaxy may become, to its future inhabitants, the entire visible universe. They might look into the sky and see only their own stellar city. unaware that countless galaxies once shared the cosmos alongside them. All the distant structures we can observe today, spiral giants, colliding systems, glittering galaxy clusters, will someday slip into invisibility. Without historical data or records preserved by intelligent beings like us, future astronomers may never know that a vast universe once teemed beyond their reach. This highlights the priceless value of humanity's current era. Right now, we live in a cosmological sweet spot, a time when the universe is old enough for galaxies and life to form, yet young enough that we can still observe its large-scale structure. We are among the few observers who can witness the expansive diversity of galaxies before cosmic acceleration erases them from view. Our era allows us to read the universe's history written across billions of light years. The Milky Way-Andromeda merger therefore serves as both a reminder and a metaphor. It reminds us that nothing is permanent, not even galaxies, and it symbolizes the dynamic spirit of the cosmos, where motion, transformation, and connection govern everything. If one chooses to see tragedy in the merger, it is only because we are attached to the familiar shape of our home galaxy. But change is the essence of existence. Just as stars live and die, galaxies grow and shift their forms. Even space-time itself evolves. In the cosmic perspective, beauty is not found in what remains the same, but in what continues becoming. One day, long after our species has vanished or evolved into forms unrecognizable to us, the descendants of Andromeda and the Milky Way will glow together as a single beacon in the vast dark. And though no human eyes may witness that night sky, the universe will continue unfolding its immense narrative, a story in which our galaxy plays just one brilliant chapter. Beyond the scientific and structural implications of the Milky Way's future collision with Andromeda, there lies a fascinating philosophical dimension to the story, one that challenges our sense of permanence and identity on a cosmic scale. Human beings naturally think in terms of personal and historical timescales, believing that the world around us is relatively fixed and enduring. Yet astronomy reveals that everything we perceive as constant is actually temporary, caught in a fleeting moment of an ever-changing universe. The constellations that ancient civilizations used to track seasons and tell their myths are not eternal. Over tens of thousands of years, the stars that form recognizable shapes drift apart as they travel along distinct galactic orbits. One day, Orion's iconic belt will no longer be a line of bright, evenly spaced stars. The Big Dipper will morph into an unrecognizable scattering of points. Nothing fixed in the sky today will remain fixed indefinitely. The impending encounter between the Milky Way and Andromeda is simply the most dramatic example of this fundamental truth. It challenges the illusion that galaxies are stable fixtures of the universe. Instead, they are travelers, drifting through cosmic currents, shaped by forces invisible to the eye. Our galaxy is not a static island, but a ship moving along a predestined route. That recognition can evoke contrasting emotions, fear of inevitable cosmic change or wonder at our participation in such grandeur. Many people, when first learning about the upcoming merger, instinctively worry that a catastrophe awaits, imagining planets being ripped apart or stars crashing violently. But knowledge helps replace fear with understanding. This event is part of a magnificent cycle, a story of renewal rather than destruction. The stars will mostly continue their existence undisturbed, and new stars will blaze into being as gas clouds collide. Worlds may form around those new suns, and life might one day emerge on them, carrying forward the legacy of creation that has powered the universe from its earliest moments. The idea that the sky itself will transform so profoundly invites us to reflect on the fragility of our own perceptions. The night sky we admire, its constellations, its silvery band of the Milky Way, the faint glow of distant galaxies, is a snapshot frozen in our era. Future beings living billions of years from now will inherit a different sky entirely. Their perspective of the cosmos will be shaped by new celestial patterns, and the stories they create to explain the heavens will differ from anything we could imagine. This raises an intriguing question. How much of our understanding of the universe is tied to our present vantage point? Had humans evolved in a time when Andromeda already towered across the sky, our sense of the local cosmos would be radically different. The concept of a distant galaxy might never have emerged. Its presence would be too obvious to overlook. Instead of seeing ourselves as inhabitants of a single spiral among billions, we might believe we existed within a grand double spiral system. Our place in the universe would feel much more crowded, the cosmos more intimate. Astronomy is, in many ways, a science of humility. It reveals that our knowledge is shaped by temporal coincidence, by the fact that we arose at this particular moment in cosmic time. We are fortunate to exist when the sky holds remnants of the universe's early history, a universe still expanding, galaxies still visible, and the faint glow of the Big Bang still detectable as cosmic background radiation. In the distant future, much of this evidence will fade from sight. The collision between the Milky Way and Andromeda will transform what is visible, while cosmic expansion will erase what lies beyond. Future astronomers, if they exist, will have a harder time reconstructing the universe's full history. In that sense, humanity's scientific discoveries are a unique and precious contribution to the preservation of cosmic memory. We are one of the rare species, at one of the rare moments in time, capable of understanding the universe broadly rather than narrowly. That awareness brings with it a kind of responsibility to continue exploring, learning, and documenting the cosmos while the evidence remains accessible. It also invites a deeper appreciation for our own existence. We are temporary beings living on a temporary world, inside a temporary galaxy structure. Yet our curiosity allows us to transcend that fleeting nature. We cannot halt the merger or alter the universe's trajectory, but we can comprehend it, map it, and marvel at it. Our observations and simulations offer a kind of immortality not for us as individuals, but for our knowledge and curiosity. Even if future civilizations never learn that their galaxy was once part of a grander spiral, our recordings of the truth may endure somewhere, waiting to be rediscovered. The Milky Way-Andromeda collision is therefore more than a distant astronomical forecast. It is a reminder that existence itself is fluid. Change is woven into every atom, every star, every galaxy. To embrace that truth is to recognize that the cosmos is not a backdrop but an unfolding drama, and we, however briefly, are conscious witnesses to its beauty. To further appreciate the significance of the Milky Way and Andromeda's dance toward one another, we can look beyond immediate astrophysics and consider how this event fits into the long-term fate of the universe itself. The cosmos is governed by vast cycles of formation and decay, and galaxies are among the most dynamic participants in this evolution. In its early years, the universe was a much more crowded place. Galaxies frequently collided and merged, growing larger with every encounter. Today, the expansion of the universe has created immense distances between most galaxies, making major interactions less common, except within tightly bound groups like our own. Yet while this merger marks a dramatic transformation for our local region, the universe on the whole is moving toward a quieter, more diffuse future. As time progresses, the expansion powered by dark energy accelerates, pushing galaxies farther apart at speeds that eventually exceed even the speed of light in terms of recession velocity. In such a future, connections between cosmic structures will be severed. Only gravitationally bound systems like the local group will remain coherent while the rest of the universe slips out of view. Long after the merger has completed and Milkomeda has taken shape, its stars will continue to evolve, shining for trillions of years until the brightest giants burn out and the galaxy becomes dominated by dimmer, cooler, stars-red dwarfs that live extraordinarily long lives. Starbirth will gradually decline as the reservoir of gas needed for new suns is depleted. What was once a vibrant system full of glowing nebulae and swirling arms of active star formation will settle into a more stable, muted state. Black holes and dead stars will increase in number, acting as landmarks of past cosmic activity. This stage of cosmic evolution is sometimes referred to as galactic retirement, where the once youthful star-forming spirals become elderly ellipticals that twinkle with the soft reddish tones of ancient stellar populations. Farther into the future, the universe may enter what cosmologists call the degenerate era, when most stars have exhausted their nuclear fuel, and galaxies are filled with the remnants of stellar evolution, white dwarfs, neutron stars, and black holes. Even then, processes continue. White dwarfs slowly cool to become black dwarfs, hypothetical bodies no longer emitting detectable light. Black holes merge and grow, while the motion of stars disperses energy until the galaxy reaches a kind of gravitational equilibrium. Life, if present anywhere, would face environments starkly different from those that nourished civilizations during the universe's energetic youth. Reflecting on these immense timescales can be overwhelming, but they also illuminate the preciousness of the cosmic moment we currently inhabit. We live in a universe bursting with light, with galaxies active and visible, with stars forming rapidly enough to support countless worlds like our own. It is a period defined by discovery and complexity, a time when the cosmos is readable to beings who dare to study it. Compared to the eons ahead, our epoch is brief, yet exquisitely rich. The looming merger between the Milky Way and Andromeda therefore symbolizes the turning of a cosmic page, closing the chapter of our current galactic architecture and beginning a new one that will influence the future shape of the universe locally. It may seem like an event detached from human experience due to its distant timeline, but it matters because it is part of the same continuous story that allowed life to emerge on a small planet orbiting an ordinary star. Every atom in our bodies was forged in the hearts of stars that once spiraled through the Milky Way's arms, and some of those atoms may have originally belonged to galaxies long since absorbed by ours. The universe writes its history not in ink but in matter, energy, and motion, and we, unknowingly, carry fragments of that history within us. The future collision will continue this pattern of remixing and renewal, scattering the elements of worlds and beings into new cosmic arrangements. On philosophical grounds, we can also take comfort in the fact that the universe is not static or stagnant. A dynamic universe is one full of potential, where the unexpected can occur and where transitions lead to new possibilities. The merging of galaxies is not an end but a transformation, the same type of transformation that once turned collapsing gas clouds into suns and planets. What arises after the merger might someday harbour observant minds who question their origins, just as we question ours. They might look up into their night sky, whether bright and star-dense or serene and elliptical, and wonder how their galaxy came to be. Perhaps they will discover the ancient records left behind by humanity, or another early species, gaining insight into the long-lost era when their galaxy was two separate spirals gliding toward one another across the dark. In that way, our studies today are not only for ourselves but for the future consciousness that will inherit this cosmos. We are early witnesses in a very long story, and our understanding becomes the memory of the universe itself. As we reach the culmination of this remarkable cosmic journey, the impending merger of the Milky Way and Andromeda stands not just as a scientific forecast, but as a narrative about our place in the universe and the grand continuity of cosmic evolution. Humanity has only recently acquired the ability to perceive such enormous spans of space and time, yet this capacity to understand the fate of galaxies billions of years in the future is one of our species' most extraordinary achievements. We have unlocked enough of the universe's laws to see beyond the temporary structures that surround us. When Andromeda finally blends with the Milky Way, the sun will likely still be shining, though its days will be numbered. Our star, currently in middle age, will eventually exhaust its hydrogen fuel and expand into a red giant several billion years before the collision reaches its final stage. By then, Earth as we know it may no longer be habitable. Whether life endures on any world in the Sun system or on other planets elsewhere in the galaxy, the cosmic environment will continue changing around it. New stars born from the merger may carry with them the ingredients necessary for life, forming planets billions of years after Earth has crumbled to dust. In that sense, the legacy of our galaxy will persist, not just through stars and gas, but through possibility. The thought that the universe continues to create opportunities for life long after familiar worlds are gone can be profoundly reassuring. It suggests that existence is not centered on us, but is far more resilient and widespread. Even if our species survives only a brief moment in cosmic history, the universe continues its creative work, giving rise to new chapters we cannot witness. That recognition encourages humility and respect for the fleeting gift of consciousness we currently possess. At the same time, knowledge of the merger highlights the remarkable privilege we have of seeing the universe in its vibrant youth. We exist during a time when galaxies are visible, stars are plentiful, and the cosmos is transparent enough for us to study its origins. Billions of years from now, observers may struggle to detect the traces of the Big Bang or understand that galaxies once filled the universe in great multitudes. Our understanding provides a snapshot that may someday become invaluable. a record of what the cosmos once was before it slipped into an age of isolation. That places a quiet responsibility upon us, to preserve our discoveries, to continue exploring, and to share that knowledge while we still can. Perhaps the greatest beauty in the story of Andromeda and the Milky Way lies in the reminder that endings in the universe are always beginnings in disguise. The spirals we admire today will not vanish without a trace. They will become the foundation of something even more vast. Their stars will continue to shine, their black holes will merge and grow, and their gas clouds will spark new suns in a luminous rebirth. The cosmic landscape will evolve into forms no human has ever seen, yet every stage silent or spectacular carries meaning within the grander scheme of existence. And though the sky of the distant future may bear no resemblance to the one humans learn to navigate, it will be no less awe-inspiring for those who look upward. If consciousness survives into those unimaginable times, it will inherit a universe reduced in visible scale, yet still rich with wonder, reminding all who gaze into the night that transformation is the fundamental language of the cosmos. So while the idea of our galaxy colliding with another may seem intimidating or surreal, it invites us to adopt a broader vision of life and time. The universe is not static. It grows, moves, merges, and reshapes itself endlessly. Nothing that exists today will remain unchanged, but nothing truly disappears either. It only becomes part of the next configuration. The future Milkomeda Galaxy, glowing with the combined brilliance of stars from both Andromeda and the Milky Way, will be a monument to this eternal cycle. Long after our species has finished its chapter, the galaxy born from this merger will continue its journey through the deepening silence of space. And just as we have sought to understand the galaxies that came before us, some distant minds may one day ponder the origins of their celestial home, perhaps discovering in ancient records or stellar relics the story of two great spirals that once danced together across the void. In that enduring curiosity, the essence of who we are may live on, woven into the same fabric of exploration and wonder that drives the universe itself. The story of the Milky Way and Andromeda is therefore not just the future of galaxies, it is a mirror reflecting our own yearning to understand, to belong, and to witness the beauty of a universe forever in motion. And in that motion, everything finds its place.